Hey, hello, welcome everyone to today's another live stream. I hope you all had a lot of fun in Ritvi's previous workshop. If you're attending and if you're just joining in, welcome. This new stream is now about a brief introduction into quantum computing. I am so excited to talk about it, and I just can't wait for more of you to join and just like get started with this. So before we can get started, just want all of you to check in on the event. You have the URL right there. So go ahead, check in for the event, register. And yeah, let's get started. Let's talk a little bit about what the whole quantum hype is about. Disclaimer, this might get a tiny bit mathematical, but I'm trying my very best to like keep the math away and just like talk about just, the whole, what it means to think about in terms of like quantum computing, what it means, what are the differences in quantum and classical. Excited to talk about all of that. Hi to everyone. Always lovely to see all of you. So hello to everyone. Okay, so basically, first I'd like to give a small disclaimer here. I am not an expert in quantum computing. I don't have a PhD in it. I didn't do my master's in it. I took a university course in quantum computing, and I found it to be truly fascinating. And I thought, what's more lovely to then just share it with the whole community, and the other people who are aware about it, have a conversation with them, and yeah, just keep it keep the conversations going, essentially. All right, so how I plan to like lead this whole thing today is we won't be doing much of programming. We'll be talking about the concepts, and then there is a whole quantum computing game that was created by Qiskit, and we'd be looking at that. So I'll be sharing a link for it shortly. Let me give you a brief introduction on Qiskit as well. So basically, for quantum computing, to be able to do it, there are like a lot of different libraries, and a lot of different companies are doing their own research on it. So IBM is doing a lot of quantum research, and they have this package called Qiskit, which is a very popular quantum computing library. And we will be using their content today to just, explore the different concepts that are surrounded around it. So I hope all of you have checked in, and I just want to like first ask in the comments if there's anyone who's ever read about quantum computing before or has like a brief idea about what that is. Yeah, so make sure to like put it in the comments what you think about it, what you know about it so far, and then let's like take those points and try to understand what is quantum computing. And this is the Hello Qiskit game that we'll be using to further understand it. Don't worry, I'm sharing the links. So it's all coming soon. Okay. Let's see. But before we start the game, I would like to also just let's do a little bit of Xcali. Okay, so we have a few comments here. First time with quantum computing, had a little hands-on experience with IBM quantum computing thing, but it was quite a while ago, so I don't remember. Only heard about quantum theory. First time for me, so it'll be a lot to learn. Well, I see a lot of good experience here. You all have heard of quantum computing. You're beginners to it. I think this field in general is very new. So as software developers, as people who don't have a lot of background in physics, I think we're all sort of trying to understand what it is. And I think this is like a great time to get started with it. So thank you everyone for joining, and glad you're like taking an interest in this. Only familiar with quantum physics. Well, that is the whole basis of quantum computing. So, well, you have the right experience there. Quantum computing always comes with like, you can't separate the physics part of quantum computing from it. And same goes for maths. So quantum computing right now, to understand as a subject, is very mathematically heavy. But what we can try to do here is try to just get more into the concepts of it, not go very deep into what quantum mechanics is, but still try to understand how these computers work, right? So let's quickly, okay. I'm going to stay here. I'm going to try to draw on my touchpad and hope that that doesn't waste a lot of time and we learn something here. Okay, so let's talk about classical computing and what you know about it, right? So classical computers, so if we look at classical computers are what we know of are made of bits, right? That's the most simplest unit of computing that we know of today. That we do all our operations using these bits. And what these bits essentially represent are just two values that we know of, the binary 0 or 1, right? And that is what classical computers build on, and even the most complex calculations happen with the help of these two values of 0 and 1 in our binary system, right? So similar to classical computers, quantum computers use something that's called a qubit. Very similar name, and technically similar to bits because it has to do computation. A qubit also represents two values, 0 or 1. But now we enter to the differences between bits and qubits. Bits are, they use more classical components to be built. So let's say even a light bulb can be represented as a bit, right? When the light bulb is on, the value is 1. When the light bulb is off, the value is 0. It's a classical unit. We can see that the value is definitely either 0 or 1. Well, qubits, they have a lot of quantum properties. So there are properties like entanglement and superposition and all these big words that change what the value of a qubit is and how a qubit differs from a bit. So because of the quantum nature of qubits, it can actually also hold the values of both 0 and 1 at the same time. And it can have different probabilities of it being 0 or it being 1. And the beautiful thing about qubit is that we don't realize the value of the qubit till we don't measure it. So it's like the Heisenberg's principle, where you can either know the position or the speed of an electron at a given time, but not both, right? So similar to that, we can perform operations on qubits, but we won't know the value that a qubit has till we don't measure it. So there are different probabilities that when we see a qubit, we can say, okay, this qubit has 50% probability of giving us the value 0 and 50% probability of giving us the value 1. Whereas there can also be a qubit which has a probability 100% of getting 0 or 99.8% of getting 0. And that is how we get qubits with value 0 and qubits with value 1. So the values and the measurements in qubit rely a lot on probability. Whereas in bits, if you measure a bit, which is supposed to be 0, after all the calculations that you perform on it, it has to be 0. There is no way that the bit can be 1. But that's not the case with qubits. Qubits can have either value. To better understand it, let's try to think of the Schrodinger's thought experiment, right? If you're not familiar with it, let me describe it here for you. So Schrodinger had a Schrodinger's cat thought experiment basically goes as that if you take a cat and you put a cat, say, in a cardboard box with a radioactive substance, right? Then over a period of time, this radioactive substance is going to decay and eventually it's going to poison the cat. But you cannot see inside the cardboard box, so you don't know what's happening inside. So for you at a given point of time, the cat could be both dead or it could be both dead and alive at the same time, because you don't know what's happening with the radioactive substance, at what speed it's decaying, so we don't know if the cat's alive or not. And you would only know if the cat is dead or if it's alive if you lift the lid of the box and you see the cat inside. So this process of us lifting the lid and checking what the state of the cat is exactly what the measurement of a qubit is. And the cat being both dead and alive at the same time when we don't open the box is the superposition property, where both states exist in reality at the same time, and then by measuring it we bring one to the surface. So is quantum computing harder than classical programming? Well, it's difficult to answer that question right now, because mostly because of how you define something as being hard. Well, if we mean if quantum computing is not as straightforward because we don't know the basics of it right now, then definitely. Also, obviously, classical programming is more, there's been more research on it. You have more everyday devices, like we are all using quantum, like classical computers every day, right? And we don't have access to quantum computers. We don't study about it from like a we don't regularly study about it. It has some different maths right now, which is not the most straightforward thing as of now, because well, we've not had enough exposure to it. So in that way, yes, you could say so. But is it absolutely too hard to learn, and like, is it like something that's super super complicated? I did not personally think that that was the case. I thought it's a new way of thinking, and once we familiarize ourselves with it, it becomes more natural and common to like think in terms of it. Okay, so since we're talking about measurement, yeah. So the two things that the cat tells us, that if you lifting the box, you can think of it as measuring a qubit, and the cat being both dead and alive, it's like the superposition. So yeah, that I hope that gives you a brief idea of like a building block of a quantum computer. And obviously we know now that our world is not classical, which is why classical theories alone cannot explain the world around us, right? So if anyone who's aware with the quantum theory or quantum physics knows that everything around us is quantum, because like all the subatomic particles have quantum nature. And yeah, which is why it's like it's a part of our environment, but we're still trying to understand it better because of the randomness that is there, and because of the different probabilities that are involved, that there is no certainty in anything. All right. So that covers our very basic intro on what's a qubit and what's a bit. So if we dive a little bit more into how we talk about it, how we write it, either in the computing world or in the quantum mechanics world, we have to take a little bit help of linear algebra, and we have to use things which are like bracket notations and stuff like that. But let's pause on that, and let's go to the Qiskit game that I was talking about, and let's take a look at what all of that is about. Okay, so I'm going to, change my screen to that and share the link with all of you really shortly right now. So this is let me make like a short URL for you for it, since this is like a really big URL. I'll just put it up here. Okay. So in the comments, you should be able to see the link to a simple game. So, went on Twitch, yes, okay. The link right now, points towards the level 2. But let's start from the level 1, and let's talk about the bits. So I'll give everyone a second to just grab their laptops or like their iPads, anything, and just put the link in and just open the textbook, and we will go through it together and sort of try to understand the concepts all at once here. But I want all of you to like go along with me, so that we if there are any questions, you can ask me here, and we can just have a conversation about it while we go. I know all of these things sometimes get like harder to do alone, because sometimes you lose the motivation. So this is the perfect time for all of us to like come together and try to understand the concepts. Yes, so this is a part of the book, but what I am working with here is the game that they've put up. So if you want like more information about, and you want to actually build proper basics and spend the time on it, you can start reading the book from the beginning. I found this book to be very helpful when I was trying to understand quantum computing for the first time. I think their explanations are really good, and they try to really get into the basics of things. So definitely recommend that. But for now in the stream, since we only have about like 1.5 2 hours, let's try to go through this game, because I think this also gives a good introduction to a lot of the concepts. And I love that we start with talking about the bits, so that we can later translate those concepts to qubits, right? So the concepts in quantum computing are actually also very like, you can find the mapping between them. Like in classical computers, you have bits. So in quantum computers, you have qubits, different behaviors, but are sort of trying to achieve similar things. And then when we come to, so in classical computers, when we do any operation, it happens via logical gates. So our logical gates are NOT, AND, OR, NAND, XOR, and they really help us to do all the complex things that we know of can actually be simplified into logical gates, which is why we're able to like achieve any of the results that we have. But again, at the same time, like it's very complex to think about it, but we can try to do very simple calculations using it. So even in quantum computing, you have something called quantum gates, and we use quantum gates to perform operations on our qubits and get the results. So it's very interesting that quantum computing right now is at a point where the programming that you do on it, on quantum computers, is very much like logical gate programming that is considered low level in classical computing right now, because we've built so many layers of abstractions that you don't have to care about what's happening under the lid right now. But with quantum computing, most of the programming that you'll find yourself doing is actually quite low level, because you're actually trying to understand and keep a proper picture in mind of what's happening with the qubits and how things are changing and what the circuit is looking like. So the circuit is a big part of how we will be performing quantum computing in the beginning, when we're trying to understand it, learn it, and while more abstractions on it are being built. So I assume most of you have started here. So this basically has a lot of like code cells that we can run. So let's just try to run them. And it's like a Jupyter notebook, but it's in their personal sort of like interface. So we can just use that here. So we see that these are the code cells. This is a very important cell to run, because from their textbook, it's using this game, Hello Quantum, and that's what we're using to understand about bits here. So let's just run that. So like we talked that quantum computers are based on qubits, and they are a quantum version of bit. It makes sense to first understand a little bit about bits. I'm sure all of you know how they work and what they are. But let's do this one tiny game. It's like very interactive, so we don't have to write any code as of now. Later on, we might have to. And it's a good way to understand what's happening. So this is their code that sets up all the the space of the experiment that we're going to run. But you can see here that it shows up like this. This one circle that we have here is actually representing a bit. And when it's black, then that means it's off. And when it turns white, then that means it gets on, right? So we know that if we have something that's off and we put a NOT on it, a NOT gate classically, then that would change off into on and on into off, respectively, right? So let's just try to choose a gate, which is a NOT gate, and we run it. We only have one bit, so let's just run it on the only bit, and we apply operation, and we see that applying NOT once will make it on. Then if we apply NOT again, it's again going to make it off, and if we apply NOT again, then it's going to make it on. So we know that how NOT will work on this one bit is quite clear. It's always the same. The probability is always going to be 100% of the bit turning on and off at this given point of time, right? So, hey, thanks for joining. Thank you for jumping in to say hi. Maybe stick around later in the session and we can like have more conversations about quantum computing. It's just good to have more experienced people here as well, so that we can have like a good healthy mix of conversation. But hey, okay, so this is how bits work, and this is how the NOT gate works, right? Now let's run the second puzzle where we work with 2 bits. Now let's try to do the NOT operation on the bit on the right, and if we do that, we see that that is now going to be on, and it's not going to affect the bit on the left in any way. So I'm saying these things right now as if they're supposed to mean anything, but you will observe a little bit in the further puzzles that it actually makes a difference, and it changes what's happening in the quantum world. So in the classical world, you see that even if I manipulate the bit on the right, it does not do anything to the bit on the left, right? So now we have a good understanding of how the NOT gate works. Now let's try this other experiment where we learn about the controlled NOT gate. So control naught is actually a very important gate in both the quantum and the classical world. So basically why I say in the quantum world as well, because we have equivalents of all the classical gates in the quantum sense as well. And we will see how they behave a little bit differently from the classical gates. Before that, we should first see how classical gates work, right? So here we have these two gates. We have these two bits. One is on and one is off. And we have a gate which is called the control NOT gate. So what the control NOT gate actually does is you have one bit which becomes it's always applied on at least two bits. You have a control bit and you have a target bit, right? So let's actually quickly switch to Excalibur here and talk a tiny bit about this gate. Just a second. All right, and okay. So yeah, sorry. Hope you all can see it, and yeah, all right. So here is Excalibur, and let's talk about the control gates. And here we're specifically talking about C naught. So basically if you have two bits, sorry, this does not define a bit. Okay, let's use this as bits. If the value of one is 0 and the value of the other one is 1, and let's say that this one is our control bit, this one is our control bit, and this one right here is our target bit. What happens when we do a control NOT here? So we basically connect these two together. Since this one is 0, when we try to, so what this will do is it will try to use this as control and run NOT over here. So this is the bit on which it would try to run the NOT gate, right? But whether it runs this NOT or not depends on the first bit. So if the value of the first bit here is 0, then the 1 remains unchanged because the control is basically off, so you don't run the NOT. But if now the value of this control was 1 instead of 0, it would then tell this target to run the NOT gate on it, and this would become 0. And then if you ran it again, this would become from 0 to 1. So that is how the control NOT works. It's quite straightforward there. So let's try to now run this experiment. We know that the bit on the left is white, which is on, and on the right it's off. So if we choose the C naught and we take the off one, so right now when we choose here, we're choosing what becomes the target. Let's just see. When you're asked to choose a bit, you're choosing which will be the target bit. So if I want to say that the left bit controls the right bit, then I can choose the right one to be the bit here. But I want to show you how the C naught would not work if the value of the control bit was 0. So let's choose the bit on the left to be our target. And we apply the operation and we see that the whole thing remains unchanged. But at the same time, if I was now to take the C naught and apply it on the right bit, so now our target is the right bit and our control becomes the left bit. And what this means is that this has a value of 1. And now this will run the NOT operation on the right bit. And if we apply operation, we get this. Now we could have, basically. So you see that this is how it goes, and we run the C naught. Again, here this is another experiment where you just get to run C naught multiple number of times. Let's try to run that. Again, let's do it on the bit on the right. We apply operation. We get the 2 ons at this moment. But now let's take, say, the right bit and, the left bit as the target. And now based on the right bit, it's now going to become off, right? So this can be done multiple times, and you can try to understand the nature of C naught. Once we are done with that, we can then try to understand something that gets a little bit more complex. So, is everyone clear about what C naught is? Okay, so now let's try to see this gray circle, right? This gray circle is trying to say that the bit value that was created on like this particular bit value was created with a random process. So even in classical computers, you have random processes, right? Like you do random number generation, and we try to do a lot of random activities. So now in that case, we would not know the exact value of that bit. It means that for a random bit, it can give us both 0 or 1 values with equal probability. So we represent that with a gray circle. Now let's look at our gates and see how we can manipulate it. So if we now take C naught and apply it to the bit on the left, then it's not going to do anything right now, right? Because on the right, we have a control bit which is off. So the control says don't run any operation on it. But now if we take the C naught and we run it to the bit on the right, we will now see a different behavior, which makes it gray. Now, why this happens is because there are two things that can happen, right? So basically, if right now we have this bit and we have our target bit, this has a mix, sorry, this has a random probability, and this has the value is 0. And so now there are two situations. The situation 1 is when the random is 0, and in that case, when we do the C naught operation, this remains 0. But then there's the other situation where if the value of the random bit is 1, then this also flips and becomes 1. So we see that the randomness is actually now the randomness of the first bit has actually been transferred to the second bit, and now the value of this can also be random, so which is why we now represent it with a gray bit. Here you saw that basically here what you saw is that the right bit was actually the randomness of the right bit is actually related to the randomness on the left, but looking at this diagram you don't really get an idea or essence of that. So for that, let's try to go to the next puzzle, where we've added a new circle, which gives us an indication of whether the two bits that we have and their randomness is that related in any way. Okay, so it's all right. Go get your sleep, and we can always watch it later. Yeah, bye. So yeah, let's look at the bits here and the meaning of this circle, which is given right here. Right? Okay. So this, when they are gray, when it's gray, then that means that it's random. If they can be used independently, which means that they disagree, then this bit will always be white, which means it will be on. If they are certain to agree, then it will always be off. Which means it will be black. And if their agreements and disagreements are just random, there's no there is no connection between it, it'll be gray. So now there's an exercise which says that try to make the two bits always disagree, which means that make the center bit be white. So you have to basically try to run different operations here and see how you can make that happen. So maybe give it a go, try to do a few operations on your own and see if that is the case. Let's try to do, so if we do a naught on the left one, we know it will still remain gray. It won't make any change there. And if we do a naught on the right one, then that means it will make it on. So we can do that. And then if we take the bit on the right, and we use this as the control to do a C naught on the left bit, let's see what we get. We don't get anything because again it's going to be a random probabilistic mixture which is going to be the same. Okay, what does agree and disagree mean here? So by agree, it means that both of them follow each other, and by disagree, it means that they don't follow each other. In a better way, it's like the value of one depends on the other, and like when they agree, that we say that it always, the value of one bit always depends on the value of the other bit. But if they disagree, it means that the value of these bits don't depend on each other at all. And when there's a randomness, then we say that okay, sometimes they disagree, sometimes they agree. Okay, so now let's try to run a C naught on the right and see what happens. The reason why this happened is because we had a random bit here, right? And then we had a 1 here. And again, like I told in the last example, when this random bit, which can have both 0 or 1 values, when you use this as the control to run the C naught, this can either remain unchanged or it can change its value and flip to the other one, which is 0, which is why when they both become random and they both start disagreeing. So yeah, there is that. Let's now move to the next puzzle so that we can move on from the bits to the qubits. This is the last one in the bits. This says, okay, so this is just a puzzle. It says, okay, so here we know that the relationship is that it's random. It agrees and disagrees randomly. And now what we want to do is we want to turn on the bit on the right, which means that we want to make it white. So if we now run a C naught on this particular bit directly, using this, it will do nothing. If it's white and we run a C naught on it, we know it's going to remain gray. So let's try to run a C naught with the target being the left bit, which would then, by our experience so far, make this bit on the left gray, right? So let's see what happens. Okay, so now we know that they both agree with each other, they're both dependent, and the randomness is not there. And now what we can do is we can just we want to make the bit on the right. So let's run a C naught on the right bit with the left. And now it is off. So we can just simply run a naught on it, on the bit on the right, and we apply the operation here. And we got the on. Did you sort of understand how that happened? And if you have a question, maybe we can like do this again, run the circuit again and see what happened. Hey Anurag, so we have just started talking about quantum computing. We've covered very little stuff right now. That is the building block of quantum computing, which is a qubit. And right now what we're running these puzzles, which tell us about the behavior of running logical gates on bits, classical bits, and we'll be moving on to qubits very soon, which are quantum bits. Why does the middle bit change when the others are manipulated? Okay, so basically that happens because when we run different operations on it, the relations between the two bits changes. The relationship that they have is not set in stone. It only represents the relationship in a given moment between the two bits. So which is why it sort of changes. I know it's a little weird, that it becomes random all of a sudden and then it's again disagreeing or it's agreeing, but that just means that in that particular moment, for those two states of the bit, they are in agreement or disagreement. Hope that made a little sense. We will now then discuss it in the form of qubits. Maybe then that will making a little bit more sense. Okay. So yeah, now it's time for the qubits. So now here we will use, now since we're using qubits, we don't call the gate a NOT gate anymore. I mean, that's not the usual reference. We instead call them X gates. But before we start playing the puzzles here, I want to talk a little bit about the mathematics, because I think that sort of sometimes helps explain these things a bit better. But I see we have a question about the bits. I see. So how can we predict the change? Do you mean predicting the change of the center circle that gets created here? Are we talking about the prediction of this? So this basically depends on the probabilities. So basically here, when we have something random and when we have one, and if the value of this say also becomes random, and the randomness depends on the value of this one, then we both know that the randomness of this depends on the value of this, which means that they both are sort of connected to each other. So yeah, that is when you know that the circle would agree and it would turn black. And if this is just random and the random value of this does not affect the random value of this, then the circle in the center would become white. How can I access quantum computers? You're interested in this. Yeah. Then how is it random? Can you be a little bit more elaborate? I've used the word random multiple times. And by random here it just means 0 or 1. Yeah. A little bit elaboration on the question would really help me answer it. Meanwhile, let's talk about accessing quantum computers. So yeah, we can actually see this here. So IBM has quantum computers that you can access, and there are obviously, so there are two ways that you can actually access the quantum computer, right? Okay, let's say 3. So let's talk about those. So if you want a quantum computer, first thing is you could just buy one, but that's very expensive and you can't do it, right? You could always get a physical quantum computer. Those exist and you can do operations on it from your own, from scratch. Very expensive. Second thing is there are a lot of companies which give you their quantum computers to use, just like there are cloud services for regular servers and hosts. So you can take space, like you can use the computing powers via the cloud for a lot of quantum computers that exist. You can use computers from IBM, you have Honeywell, there are a lot of other companies giving you that. The third thing is that you can, when you're trying to learn quantum computing, you can simulate what a quantum computer would do on a classical computer. So we can do that for about 28 to 30 qubits. If we had to simulate that big an operation, we could probably do that. I think IBM allows you to simulate that much. But after that, we run out of processing power. And for more complex calculations where quantum computers are actually faster than classical computers, we obviously cannot simulate that on a classical computer. This is something I don't know about. I don't know what's the operating system used in quantum computers. Like I said, we do a lot of calculations on the server level. And I know how quantum computers do operations. So I can talk about that, but I don't know if there's an operating system working on them and how that works. If we are to talk a little bit about the quantum computers and how they are made side of it, let's do a tiny bit of that. So how qubits are created, right? So there are a lot of different ways of creating qubits. Because there are a lot of different properties, there are a lot of different things around us which have quantum properties. So any of them can be used to create a qubit. Right? So this is funny. Maybe Windows 11. Short thing. Okay. So yeah, let's talk about quantum computers, how qubits are made. So if we know, that an electron has an orbit spin, right? And the orbit spin has, like what we've studied, it has a value of -half and +half. So the spin property of the electron can be used to create two qubits. A qubit with two different states, which is 0 and 1. So we can say that the -half, or let's say up and down, right? The up property of the spin can be represented as 0, or up can be 1 and down can be 0. So what this means is that the electron, it's like one single, the single electron can represent two different kinds of states. And as you know, that till the time you don't measure the spin of an electron, you wouldn't know whether it is 0 and 1, which is when it is in a superposition of both the values. That is the nature of an electron. So we can try to stabilize that like the electron spin and then create a qubit out of it. Similarly, we can do the same thing with photons, and there are so again you can't just isolate an electron, so we use different elements to make quantum computers with it and then create qubits out of it. Let's think of other things. There are also because isolating these subatomic particles means that atomic and subatomic particles means that you have to put them in a super cool environment. There should be like no reaction between them, because if there is even like a tiny bit of reaction, you can get noise and errors in your calculations, and your 0 can suddenly convert to 1. So you also have to keep in mind that there should be enough of an energy level difference between the up and the down states. Like the 0 and the 1 states should have enough of an energy difference so that like even a slight difference doesn't change your state from 0 to 1. Because then what would end up happening is that, say you have a series of bit data, right? Bit data looks like this, for example, and let's say you had this information, and if one bit just if a little bit of more energy is provided to that one electron, and suddenly it excites and changes state from 0 to 1, now what you have is like completely new information, and our old information gets lost, which is what makes it very hard to create quantum computers, and which is why it's hard to stabilize them to make sure that they don't have errors, or they are giving us results which are error mitigated. And there are a lot of error correction methods that are used to deal with stuff like this, because bit flips happen quite commonly in quantum computers. So you have error correction codes and error mitigation techniques to get rid of that. But on a principle basis, this is how it's done. There is also NMR quantum computing, which can be done on room temperature. But the problem with it is that it's not very scalable. So what this uses is, let's try to maybe get a video of it here, but maybe you can watch it later. Nuclear magnetic resonance. That's what these quantum computers use, and they can be run on room temperature. But again, there are issues with its scalability. The interesting thing is, here in NMR computers, one molecule itself acts as one quantum computer. So you combine multiple molecules together to then create one giant quantum computer that can then be used to perform operations on. Exactly, no wonder it's expensive. There's again a lot of research is happening in physics and chemistry right now to make quantum computers work on room temperature and make them more accessible. And because the most expensive part of making quantum computers is the cooling. I can show like a picture of IBM's, don't know how to find it, just a second. IBM quantum computer cooling chamber or something. There is a huge device that is used to cool. This is where the cooling happens to then stabilize the electrons and to just isolate different qubits and then perform calculations on it. So yeah, you can see that these are all expensive devices, and there's a lot of science behind it, and basically a lot of research is going on here. Exciting stuff. So yeah, I was talking about, this is how qubits are made, and let's say we use an electron, and now if we want to perform calculations on it. So what are actually quantum gates? Quantum gates are like an electromagnetic pulse that is sent to, say, the electron to change its spin in a different way. So that is how gates work. So quantum gates work by electromagnetic waves that are sent out. That is actually a quantum gate. So yeah, I don't know about the operating system, but this is a little bit I can share about what is a quantum computer and what does it physically mean for something to be quantum, and how a quantum computer can be created. Not like we can sit at home and create it, but yeah. So yeah, I wanted to now discuss a little bit about how we represent it, how we represent the different states, and how we write about it. So very commonly, if we have the states 0 and 1, they're actually given this notation. You'd see it very often in quantum mechanics and quantum computing. And this notation, sorry, this is not an I, this is just a 1. Oh, by the way, two mathematical topics that you should be pretty familiar with if you're trying to learn quantum computing is linear algebra and complex numbers, because they are a very important part of all the mathematical calculations that happen here. Right? So these are the two different states. This notation is a bra and ket notation. So if you have any, say, a vector, and you represent that as this, that is just a column vector. And if you have a vector and you represent it like this, right now I'm assuming that you all are aware of what vectors are and what matrices are. If you're not, I'm so sorry, can you please Google it? And this is a row vector. So this is a ket notation and this is a bra notation. And these are very commonly used to represent quantum states. I just had an exam on linear algebra and scored pretty good on it. Yay! So then you're familiar with all of this, and it should be easier for you to follow any textbook that you read on quantum computing. I won't be doing a lot of linear algebra here, so don't worry about it. Okay, so now the 0 state, basically what the state represents. So in quantum computers, qubits have something that's called a state vector, which has, luckily, the great thing is that since we're only dealing with two values, the linear algebra that we have is quite simple in the form that we deal with like 1/2 vectors or like 2/2 matrices. So relatively like simpler stuff in the beginning, so it doesn't overwhelm you. So we have these it has two values, let's say A1 and sorry, I should remove these lines. Yeah, it has two values, A1 and A2, and these both indicate the probability of this qubit measuring 0 and this qubit measuring 1, right? So yeah, if we have a 0 qubit, we know that the probability of it getting 0 is always 1, and of it measuring as the value 1 is 0. Now this is obviously idealistic, and I'm not saying that this always happens. It's possible that in a real quantum computer, the probability of 0 measuring 0 is 0.999998. So yeah, right now we're just talking about idealistic theoretical terms, which is never the reality. And in the case of 1, the probability of getting a 0 is 0 and the probability of getting a 1 is 1. Which then also means that it's possible to have a quantum state which looks something like this. Since we can define the probabilities of getting 0 and 1, we can always make it look like this, right? The only thing that you have to keep in mind with state vectors here, that they should always add up to 1, right? So another way of writing this is, so if we were to define any arbitrary state phi and say we didn't know what their probabilities were, we would take an amplitude of them, which is basically a square root of the probability of it actually getting 0 and 1, alpha. And we would say, since we know they can either be 0 or 1 at, like, we know that the quantum bits are, at the end of the day, always going to, when we measure them, give either 1 or 0 as values. And since we know that 0 has this matrix form vector form, and 1 has this vector form, we can sort of see here that the state, any arbitrary state can then be written like this, which would mean that the the vector of this looks like alpha and beta. Sorry, this and this. The reason why I put, actually I don't think I got that right. The thing that you have to keep in mind that should happen is alpha square plus beta square should always give you 1. This is one thing that needs to be true for any state to be called a quantum state. That is the states that qubits can exist in. So that's the idea there regarding the mathematics. And if we talk about the different quantum gates that are there are 2 to 3 things to keep in mind, right? The first thing is that if we talk about gates that are applied just on one qubit, so like we saw the naught gate is applied just on 1 bit. Similarly, we can have single qubit gates which are applied on just a single qubit, right? So then those mathematically will be represented in a 2 by 2 matrix, and this matrix must be unitary. My god, this is turning into a math lesson. I am so sorry. I was trying very hard to not make it one, but it's really hard to talk about quantum computing and not get into the mathematics of it. So this matrix needs to be unitary. Why am I putting myself through this? Yeah. This was a unitary matrix. And this needs to be 2 by 2. And yeah. So why do we need unitary matrices only? Like, what's the reasoning behind that? Okay, so why that's the case is because any operation in quantum computing must be reversible, which is not the case with classical computing. In classical computing, you can do operations and then it's possible to never retrieve the original value. But in quantum computing, whenever you perform gates on qubits, they always should be reversible. So if I put a NOT gate on 0, I should be able to reverse that gate in a way and get the same value. If I put another gate on it, I should be able to reverse it in some way and get my original value back. So it's important for these matrices to be unitary. What that means is that the conjugate adjacent of that matrix multiplied by the matrix itself gives us the identity matrix. Which also means that, yeah. And then in some cases there are some like interesting math that happens and that makes our life easier, but we're not going to get into that right now. But there's something you should remember. A conjugate, what this means here is that you take a transpose of the matrix and then you conjugate it. So conjugation works with complex numbers. So if we had, say, a plus ib, the conjugate of this would be a minus ib. So if you had a matrix here, just giving a small example, if you had a matrix that was, say, 0, 1, 2, 3, and you had to calculate the conjugate, if you had to calculate the conjugate, why does it think that I want? Oh, okay. Yes, brilliant. So if we had this matrix and if we wanted to calculate the conjugate of it, nothing would change because conjugates don't apply on real numbers. But if instead of 1 here we had I, and if we calculated the conjugate of it, then this I would become minus I. And obviously if we were to calculate the adjoint of it here, then this would become a transpose. So this would become minus I here and the 2 would come here, right? So when this condition is true, this particular condition, then we know that we have with us a quantum gate, and then that 2 by 2 matrix can be used in any quantum circuit, right? All right. So now that we've talked a bit about qubits and quantum gates and like how to represent it, here is your first puzzle to try. Okay, so let's run this. Let's hope it runs. Okay, I'm going to restart this and run this particular cell again. Just refresh it. Okay. Took us directly to puzzle 1, but like, let's try. Run. And setup has started and setup is complete. Okay, so now we head to level 2 and we try to run a NOT gate on a qubit. Okay, so let's try to just go along with the puzzle and do what it says. So let's say apply the X gate 3 times on a qubit. So we do that, we take the qubit, we apply operation, it turns from on to off. Again, we take it, we apply it, goes back from off to on. And similarly, if we apply it again, it goes back from on to off. So it's the same behavior that we saw in a bit that's being repeated in a qubit with the help of a NOT gate, right? So let's go further. The 2 circles that were represented here actually didn't represent different bits. Instead, they represent the same qubit. So these are basically just like bits are limited to 2 values I mentioned, so are qubits. And whenever you will extract an output from a qubit, like I said, by extraction I mean the measurement that I was talking about, then we will get a value of 0 or 1. There's going to be no probability there, there's no superposition, there is no mixture, it's just one value that you're going to get. But everything happens before the calculation and the measurement has been done. And the value that you get actually depends on how you try to extract it. So there are different ways of measurement, and if you change your way of measurement, then the value that you get is actually going to change, which is why measurement is such an important part of quantum computing. It's like the last thing that you do, but how you measure really changes the value that you're going to get, right? So right now, so there are 2 different kinds of measurements. One is called the X measurement, and actually there can be measurements in any various types. So sorry to say that there are only 2 types of measurements. You can measure it in various different ways. If you are familiar with the concepts of linear algebra, then you would have heard of something called a basis. So that is what it means to change a measurement here. We change the basis in which the calculation is happening and we get different answers accordingly, right? Most of this stuff happens in a computational basis, which is in zeros and ones, which is called the Z measurement. And then we also have the X measurement. So like we said, the bottom circle would represent, so here the bottom circle represents the measurement that's done on the Z basis, and this top one represents the measurement that's done on the X basis. Sorry, the X gate. So yeah, so the color of the circles mean exactly the same thing. The gray circle means that there is randomness. It can both be either 0 or 1, and the white or black circle mean that they are 0 or 1 respectively. Okay, so we run this here, and if we try to, it says turn off the Z output. It's very simple. We just do the X operation on this bit, which is the only qubit on which operation is available, and we have turned it off. And if let's try to do here. Now we've just changed the side where it is, and again if we have to, again it's the same thing that they're asking you to do, to just turn off this bit, which is the Z measurement bit, qubit, and we apply that here and we've turned that off, right? Now they are introducing a new gate, which is the edge gate, which in my opinion is one of the most important gates that we use because it helps us create superpositions. And in this example, they're going to show how the edge gate is used to swap values. But if you, okay, so if you take a qubit, let's say you take a qubit which has initial value of 0, And if you apply this H gate on it, then what it actually does is, if you go ahead and measure it in the, we do a measurement which is in the computational basis, which is the Z basis, and if you find out the value, obviously when you run the actual measurement, it's going to give you either value 0 or 1, and that happens because of something that the edge gate does, right? Because if the edge gate was not to be here, then most likely all the time the measurement in the Z basis would only always give you 0, it would never give you 1. But the edge gate does something with the qubit, which is sorry about that, which is basically convert this qubit into a superposition of 0 and 1, and the state would then, sorry for my horrible trackpad handwriting, would actually make it like this. Here you can see, if you calculate the probability of getting 0, it's, you take the amplitude attached to it and you do the square of it, and similarly you get half here, and this is similar to the probability of getting 1. Okay, so this is how that happens here. So this is what the edge gate does. Edge gate creates a superposition which further changes the state. So mathematically, if you then look at it, you can apply the edge gate here again, and what this would do is that it would create a superposition of 0 here and a superposition of 0 here. So let's look at what that would look like, right? So now we have, what I'm talking about is a situation where we create a edge gate here as well, right? And so in this particular instance, when only the first gate has been applied, this is what the state would look like. Not that this is what it would measure out to, but this is what it would look like. And then if we apply another gate, and if we try to calculate what that state would be, so then this 1 by root 2 would have become 1 by 2, and here inside of it we would have this distribution. So what it does with 0 is it creates a mixture which looks like this, a superposition which looks like, sorry, this is not a mixture, this is a superposition. And in the case of 1, what it does is it creates this. So this is what it does here, and this would this is what our state would be like. And then when we run a measurement on it, we can get 0 or 1 again. Sorry, and here when we write 0 and 1, it's actually shouldn't look this way. Sorry, this is very inappropriate to put. It's actually only 0 or just 1. Right, that's what it measures out to. So here also it will measure out to 0 and 1, and we can calculate the probability of getting each by just doing a square of the amplitude that's attached to each value. All right, so just we have that, and yeah, sorry, that got a little mathematical there, but I hope we understand a little bit about how an edge gate changes a state that we have. So now here what we're trying to do is it wants us to run the edge gate 3 times. So we take the edge gate and we run it on. Okay, so now we won't call it the left bit or the right bit anymore. We're going to call it Q0 and Q1. So the bit on the left, this is called Q0 and this is called Q1, right? So we run Q0 and we apply the operation. It shows that the states flip. This happens because of okay, so when you actually try to run these, so if you have a state that looks like this, and if you try to run a similar multiplication on it here, you would see that the the value of the first bit actually changes, and similarly it flips the value of the second one. So here the edge gate is actually flipping it, and you can see it again and again that a flip's happening. uh, this is now, we've ended up creating a circuit, and I already discussed that when we were creating it. This is what circuits look like, right? That if you have different qubits, you write them down, and then whatever operations you want to apply to it, you start putting those gates left to right. Okay, so that was a bit of stuff that we covered here. Do we have any questions? Can we actually bring on some questions that you all have, and we'll take a small 3 to 4 minute break before we continue doing more puzzles. This I have somehow covered like a bunch of random different stuff regarding quantum computing in the past 1 hour, so it's very likely that you feel a little bit confused, you feel things are a bit all over the place. So if you need some clarifications or you want to discuss some things that you don't understand right now, please go ahead, put them in the comments, and we can talk about them. So yeah, please put your questions and comments, and meanwhile I will go and take a tiny 2 minute water break. Be right back. Hey y'all, I'm back. So I see one question from Anurag. This is a bit about the future, so I will discuss this towards the end of our session. I would love to actually dive deeper into this, and glad to have some interest about that here. Yeah, so if you don't have any questions about what we've been doing so far, let's jump back into it and solve puzzle 5. And I'm not sure if we will be able to go through all the 4 levels, but I hope that we can at least make it to the 2 qubit gates and try to understand what they are, right? So now let's look at puzzle 5 and what it says. That when the Z output is certain, so let's run this. The X gate simply flips the value. But what if the Z output is random? So what would happen, right? Let's try to see what would happen if we apply X gate on the Z bit. Sorry, it's not the Z bit. Okay, if we apply the X gate on the bit that is being measured in the Z, like which has like the Z measurement, what would happen then? Right. Right now we are applying we're applying the gates to Q1, which is this. So let's run the X on Q1, the right bit, and we apply the operation there. Actually, sorry, it's this one for some reason. And this. And now if we run superposition on Q1, we see that they flip. So, so sorry. Let's actually try to run this again and see what would happen if we flip the order of running the X gate and the edge gate. So what if we put the edge gate first? We see that they flip. And then we run the X gate on Q1. So you can see the difference here. The edge gate actually helps us to flip the values. And now if we apply another edge gate on Q1, we can see that the values end up flipping. But this is not the result that we were looking for, which is why it doesn't give us a success, which means the operation that we did in the beginning was the right one. But we're just trying to see how it behaves differently. Okay. If you actually look at this, then we will see that it's actually just random if we run it multiple times. So the randomness is always not visible at the first glance, and we run it multiple times to be able to see that. Sorry, I ran the same things, so it's going to happen that way. And we run this again, and now on Q1 do this, and yeah. Yeah, so it's a little bit of playing around with the gates. Again, this is more in the game format, so it's not exactly how quantum computers work, but it's sort of giving a visualization for. Okay, these questions are interesting, but it's very different for when you're programming with quantum computers. The best practices are not similar to what happens when you're coding in a classical computer, because we're talking about two very different ways of working there. So again, we'll talk a little bit more about how you can do something in it and talk about it further. For now, if everyone follows the puzzles, we can actually try to understand what goes on in a quantum computer, because that is the most crucial way of programming on a quantum computer at this moment. Like, you use the circuits to program. That is how it would work. So if we run this, so in the previous one we saw that the X gate flips the Z output, but it has no effect on the X output, right? So now we have a new gate, which is the Z gate, which can actually flip the X output. So let's try to do that. So we have operation Z for Q0, which is this. So if we run it here, uh, q0 is, I'm so sorry, I'm just going to like go back and just cross check what q0 and q1 mean. Yeah, the one on the left is q0. Oh, the one on the left is q0 and one on the right is q1. Okay. So let's run this again. And q0 is this. So we are running an operation on this right now, right? So yes, if we put the edge gate on it and if we apply operation, this will flip. And now if we put the Z operation on it, again it'll not do anything to it now, because now it's a random value. And if we just directly ran a Z gate on it on the first qubit and applied it, it would flip its value. So the X gate flips the Z output and the Z gate flips the X output. This might seem like a strange way to name things. It is a bit strange, but it'll make sense more in the future about what they're doing here. So now let's try to combine a few gates and see what they can do. So this is the qubit that is being measured in the X measurement basis, and we try to do two different operations here, Z and H. Let's try to like run them together. So if you first do Z and nothing changes, and now we run the H, which would flip their values, right? And again, if we do Z on it, then it should flip the black to white. And yeah, and again we can try to do an edge, which is the flip, and we get the new values. And yeah, that's how we can sort of understand what the gates are doing to our bits in this particular puzzle. So X outputs are mostly always random when the Z outputs are fully on or off. Here we can see that when Z is on or off, X is always random. Qubits can never simultaneously be certain about each kind of output. If they are certain about one, then other must be random. If this wasn't true, we would be able to store, use the X and Z outputs to store 2 bits. This is more memory than a qubit has. Despite the fact that we can extract an output in multiple ways, we are nevertheless not allowed to store more than a bit in a qubit. This here is just talking about how what we are, yes, exactly, right? X and Z outputs here, what they mean is the measurement that's happening on a different basis. So what has happened here in this puzzle is that they've tried to simplify a concept that is actually a little bit complicated, but the simplification has ended up making it a little bit more confusing. X and Z output, what they mean is that if you have a qubit, you can measure it in 2 different ways. You can measure it in different bases, and that will give you different values. So if is anyone, no, that is all right. I mean, it's a fair question. Let's come back to this. So what a basis does is it helps to transform, like if we look at in the form of like linear algebra, right? Then what it means to change bases is just to say that, let's say we have a normal coordinate system where our origin is 0, 0, and we're like starting in a normal coordinate system. Now I say that I want to skew this system a little bit. I want to change the position of the origin, or I want to like just rotate it around a bit, and I want to now use this new plane that I have as my normal plane. Like now this is the plane that we should be doing all our calculations in. So changing that plane in which our calculations are done is called changing our basis. And so that is exactly what happens in quantum computing measurements as well. That when we have a qubit, we can measure it in any basis that we find fit for our purpose. So X and Z are actually 2 different kinds of bases on which the measurements happen. Right now, a lot of the details around that is hidden and it's abstract here in this game. So for the purpose of just moving forward here, let's understand that X and Z are just 2 arbitrary names given to 2 different ways of doing measurements, the details of which are hidden from you right now, but you can read up more about it in, let me show the chapter. There is, let's see, on the side here, there should be, maybe it's not explicitly there, but in the first chapter, like in the first section itself, there is a subsection on measurement, which can further better explain what different x and z basis measurement mean. So yeah, bit confusing there. Now what we want to, like, now it's just a puzzle, right, where what we want to do is we want the x output to be off and the z output to be random. Sorry, the x output to be off and z output to be random. So what we want to do is like first flip them. So flip them in the sense of like swap them, and then we have this to be on, this to be off. So this is the one being measured in x basis, and this is the one being measured in the z basis. All right, so you can just read the intro quickly here. So all right, okay. Here what they have done is they are saying let's increase the certainty, which means when we increase the certainty, it means that we are changing the probability. So the gray means that the probability is always equal between 0 and 1, which is why it has like a mid gray color where it's half white and half black. Now if we change the probabilities, which means if we increase the probability of 0 to be higher than the probability of 1 of measuring that qubit, then we can change the representation of the color. So a darker circle is more likely that the output will be 0, and a lighter one, it's more likely the output will be 1. So if it's lighter, then that means it has more white, which means the output is more likely to be 1. And if it's darker, that means it has more black, more likely to be 0. So now we can think of the gray bit as a 0. No, okay, so the color actually represents the value, and the x and the z output depends on the location of the bit here. So here what this means is that the one on the top, this bit, is actually the z output, and this on the bottom is, I'm so sorry, the one on the top is the x output, and the one on the bottom is the z output. So even the z output can have the gray colored circles, and even the x output can have the white or black colored circles. Does that make sense? I'm loving the career questions on quantum computing. We will get to them in about 15 to 20 minutes. Before that, let us also focus on the concepts that are going to help you have a career in quantum computing. Okay, glad that makes sense there. Thanks for following up. And yeah, let's look at the next puzzle now, where we have slightly changed the colors. So I think this is all completely black, but now let's run the Z on the Q1 and apply the operation, and it becomes, I can see the slight change here, like things are not completely black and white anymore. The probability has shifted a little bit, and that is because you can see here that they have changed the conditions here of initialization. So initially, when we were initializing, we had given it a H state and a 0 state. H state basically represents a state that is, similar to this state that we have here. This is what it means to be initialized in the H state here. And before, we also had we didn't have any initializations, or we had initializations for H being 0 and Z being 0. But now here we have switched things up, because even with H, we know that the probabilities of 0 and 1 are equal. They are the same. But here we have changed the probabilities. We have added a rotation here by pi by 4, and the success conditions have then changed completely, right? So yeah, we can then do an operation on Q1, which is just going to flip it, and then we can again run the Z on Q1, and it's going to give us like both of them are not completely white now. They have like probabilities where the probability of getting 0 is higher, and you can see it's like about because this is where it knows that it's ending. So right now we know that the success here of getting probability of getting 0 is 0.707. Also, another interesting thing about probabilities in quantum computing is that they can have negative probabilities also, which is why, sorry, it can have negative amplitudes as well, which is sort of like, okay, let me use something. All right, so there is a very good explanation here that we can use. And if you want to, if you want to read a good experiment on understanding the differences on quantum and classical computing, this coin toss example is also a very good example. It uses very little probability to talk about it, but then it all starts adding up when you read the calculations. So this is a good read to go there. And here it talks about the probabilities with negative numbers and how the negative probabilities are handled. Sorry, here this is not a probability, this is the amplitude that we have discussed here. So this is what we call an amplitude of a qubit. So we have mentioned that this amplitude can be negative, and because we ultimately calculate the probability by taking a square of this amplitude, which is what allows it to be negative. And then for this we can run the circuit and see how we worked on it. So here we saw that on qubit 1 we ran a Z operation, then an H operation, and then a Z operation again. Note that the Z and X gates that we run here are different from the Z and X measurements that we do. It's not the exact same thing. Okay, now we are on puzzle number 10, and it's again relatively simple here. We want to make the Z outputs random. So the output that's on the bottom here, these are the Z outputs. So what we can do is we can just flip them with the X ones, and we will get the random outputs here. So run it on Q0 here, and then again we take the H and we run it on Q1, and here this is exactly what I wanted. And then we can see the circuit for it, and we saw that both on Q0 and Q1 we ran the H gate, which flipped its value with the X measurement. Okay, so now they're introducing more puzzles, and let's try to see the meaning of them. So one of them we've already seen before in level 1, this one, which shows how much the two values agree or disagree with each other. There it kept track of whether the 2-bit values would be certain to agree or disagree. Here it does the same job for the Z outputs of both qubits. So yeah, only the Z outputs, these ones that are in randomness right now, and we will understand further what the top 3 mean. So sorry, we run this, and what we want to do is we want to make the Z outputs certain to disagree, which means this should become white, right? So let's go here and let's flip them, and I think we go here again and we flip them, and right now they're certain to agree. So what we'll do is we'll take the X gate, we'll put it on Q0, and we'll apply the operation, and now we know that they're always disagreeing because there's no way these two are ever agreeing with each other. Yes, it is the truth table, exactly. This is like a truth table. It's a truth table is sort of very important as a concept in quantum computing. Just that it works a little bit differently, and there are more relations added to something. Yeah. Okay. Then we can again draw the circuit for this, and we see this here. And now let's again, these are just puzzles. These are like math questions we're doing by whatever knowledge we have gained about quantum concepts. Now we have to make the X output certain to agree, which is this and this output. And we want to make them agree with each other. So again, what we'll do is we'll flip them. So we'll run this on both the operations here, and the X bits need to agree. So we'll just flip either of them. So I can either flip Q0 or I can flip Q1, and I'll just use a Z gate for it. And if I just do Q1 and apply it, it didn't work, because we saw this before, that for an X measurement value to flip, we actually have to use the Z gate on it. And we do that and we apply the operation and they flip. And this, so now we see that the circle on the top here, this talks about whether the X measurement qubits agree or disagree. So that is happening here. Here we know they're always in agreement, or by always we mean right now in agreement. Yeah, so then from that, let's keep on going to the puzzles. I don't know how many puzzles we have here. We have 15, so we have 3 more puzzles to go. Okay, now we want to make the X output for Q0, which is this one, certain to disagree with the Z output for Q1. Sorry, so Q0 is this, Q1 is this. We want to make the X of Q0, which means this, disagree with Z of this, right? And I think this circle here would be defining the randomness of it. So what we can do is we can flip these two values. So for Q0 we can run, and does it say always disagree? Certain to disagree, right? So we flip these two values in Q0, we apply the operation, we get this. And right now, see, like I said, like this circle is talking about the agreement of this and this. So right now they're agreeing because they have like the same value. We wanted to disagree, so what that means is we'll take the Z gate and we'll put it in Q0 and we'll apply. And yeah, now we know that they are always in disagreement. Now here we say turn the two Z outputs on as much as you can. So these two right now have, like, you know, they are not exactly black. So we so they're not completely off, but we want to make them as white as possible. Yeah, that's all right, which means like we will understand we have 25 minutes for the next session. So we will probably talk about the 2 more puzzles, finish level 2, which would have been a big accomplishment to achieve in 2 hours, by the way, and then take a few future and culture related questions. But thanks for the heads up there. Thank you. So now let's try. Now if we are to basically make this as on as possible, let's try to, one easy way that to see here would have been if we could just flip it, and we know we could just turn it on. But let's apply the X gate on it, which would mean that we're applying naught to it, because right now it's off and we want to make it as on as possible. So we can just do the on gate on both of them. And sorry, I did apply it on the same gate, which was the wrong thing to do. Then we take this and we apply it on the Q1 now, and we apply the operation, and we've made it as on as we could because it just flips it. So right now, if we initialized it from this state, it's going to flip it as much as it can. Like, just give it a. And here we can see this was a bit incorrect. These two were not needed. So just these 2 X operations would have been enough. Now this is the last puzzle of level 2, where what we have to do is we have to turn off the X outputs, which is these outputs, and we turn them off. So how we do that is we can first, again, we want to turn them off, right? So we can just first flip both of them and flips the values, and then we can turn them off by doing the naught operation on the X measurement. And this, and voila, we see that they are off and they are in agreement here. Yeah, so we have basically gone through what two qubits look like individually, how we can manipulate them together, and what like making a circuit out of it looks like, right? So we have learned quite a bit about two separate qubits. The next stage actually talks about working on two qubits together at the same time. So when we did level 1, we did the control NOT gate, right, where we used two different bits, but we applied one single gate on it. We had a control and a target. So similarly, we have other two qubit gates which can be used to um we have other two qubit gates which can be used to perform calculations collectively on two qubits. Because so far what we've been doing, if you look at the circuits, which is a great way to just look at it here, is we've applied operations solely on the qubit 0 and on qubit 1, right? We've applied an edge gate and a z gate. But what can be applied more is you can actually like combine. We can have a gate that covers both of them. And actually, two qubit gate is not the end of it. If you have n qubits, you can have one gate that performs n qubit operations also. So just grows on from there, and it's quite interesting like that. Definitely you should try to complete the two other levels of puzzles, and you can always hit me up with questions. Let's now take a last round of questions that we all have, and yeah, you all can like head over to the next workshop. Okay, so I'll start on from here. About I want to learn to program in a quantum computer. What will be the correct ways for this? Are there any jobs available for the same, and how to reach them? Okay, so to understand how to program in a quantum computer, you should definitely, this is a good place to start, but this focuses very heavily on Qiskit. If you don't want to do that, there are other books out there. The Bible of quantum computing is obviously a book written by Nielsen and Chang. That's called Quantum Computation and Quantum Information. But this is a very dense book. It covers a lot of information. It starts from the concepts of linear algebra and goes on to cover very, very complex concepts and algorithms. But if you are very deeply interested in the subject, then this book is a must have. Like, it's a good reference book to have around if there are ever any topics that you don't understand properly. This book is going to help you a lot with it, right? But then this is for someone who wants to mathematically and computationally involve themselves in quantum computing. But if you want to read about quantum computing as a casual reader, there is a book called Quantum Computing for Everyone. This actually has a very nice sorry, let's remove the PDF here. This is a very good introduction for people who, like, this is a book for literally, as it says, quantum computing for everyone. Like, this Chris Bondad actually explains concepts in a very easy to understand manner, and it's a lot of fun to read. You can actually like read it casually. It's not super intense or anything. I mean, it's not super intense in the way that Nielsen and Chong is, but it does cover all the basics that you would need to know to understand quantum computing. So, yeah. So relatively simple. It's not very thick. It just has like 200 pages, which is very light for a book like this. If you come from a more computer science background, there is another book that I'm trying to recall. I think it's called Quantum Computing for Computer Scientists. Yes. So this is a good way, like, this book basically gives a good introduction to quantum computing for people who are more involved in the classical computing manner and need like a perspective shift and don't want to go very deep into the quantum mechanics. Because when we're studying quantum computing, it's very easy to like dive into quantum mechanics and then get lost in the physics also of it. So yeah. But again, I would say the Qiskit book is also great. There is a textbook there that you can try it. And if you just read the basic concepts here, this actually covers a lot of things. This was basically all of my bachelor's course curriculum. So we studied all of this. So you can always like go ahead and, study all of that. Yeah. So that would be about how to study about it. I wouldn't recommend directly trying to jump into programming anything here, because you will just be lost because you wouldn't understand what are the basics, what to do, what's happening. So much of it is happening on like this circuitry level that it'd be a nightmare. So first try to understand what the notations are, which is the bracket notation, and then try to understand how what's the little bit of the physics behind it, then try to understand the different algorithms that have already been written on it, the math behind it, and then you can hopefully begin to program for quantum computers. Are there any jobs available? I guess there are plenty of jobs available in this field. You can just also go to IBM careers. Then there are other companies like Xanadu. There is Honeywell. There are obviously also Google is also doing a lot of work in it. But from what I know, IBM, Xanadu, and Honeywell have jobs in the whole sphere. And then there are again a lot of smaller startups which are trying to use quantum computing. So if you have more experience trying to work on it, like program on it, or you understand it, so more companies are hiring people. And you don't, okay, so that's the companies that are there in this field. Another thing is, say for example, there are different levels on which you can get involved. So you can obviously get involved in the education, which means you can become developer advocates for different companies and try to educate people in quantum computing. Qiskit, I know, does a lot of work in that. You can see they have these series called Global Summer School, and then they run hackathons, and there's a lot of stuff there. But apart from that, when you join as a programmer or developer, there are 3 levels in which you can involve yourself in the field of quantum computing. The level 0 is the one where you get involved in creating the hardware behind quantum computers and how to do like the calculations on it. Like I talked about, physically some computers use electromagnetic pulses, things like that. You can get involved on that level. The second level is where you try to actually build algorithms that can be used on quantum computers. And the third level is where you can take those algorithms and then apply it into real life scenarios. So if you go into whatever is happening in quantum computing these days, you'd see that a lot of operation is being found in quantum chemistry. So a lot of pharmaceutical companies are looking to use quantum computing because it helps with simulation of molecules which have a quantum nature, which cannot be simulated in a classical computer because their nature is just not quantum by nature, right? And then they help. Obviously, there is the whole cryptography space. But I don't think I have enough time to cover everything that's going on there, in the sense that while we have algorithms right now to break our current secure cryptography algorithms, we still haven't reached a space in quantum computers where there are systems stable enough to break the classical algorithms yet. But then, because at the same time there is a possible there's a foreseeable in the foreseeable future, it's possible, maybe not in the foreseeable future, but like a few decades from now, it's possible for us to have more robust and fault tolerant quantum computers, which would mean that we would then need quantum cryptography. So quantum cryptography is also a very good application of quantum computing, and where you have jobs. And again, because it's such a field which has not become too commercialized yet, there are a lot of job opportunities in academia in doing research. And again, you can do research with either universities or with industrial organizations. So that is what most of it that I am aware of in this field. You can always reach out to more experts and know more about it. So sorry, here when it was flipping, sorry to go back to that puzzle, here when it was flipping, it was actually not flipping the qubits, because this thing here, sorry, I lost the game. No. All right, let me quickly just run it for you because I want to address this question. Yeah. So waiting for it to run. Meanwhile, I'll take more questions. Again, like I think I already discussed this, that there can't be any best practices per se. We just need our circuit size to be small. And that's, yeah, I mean, there are a lot of things involved here right now which we haven't even scratched the surface of. So hard to give any best practices recommendations right now. Do you have any reference resource links in order to start learning quantum computing? Yeah, so like the link that I've already shared with the audience about this game. On the left hand side, you can see that there's a whole course here that you can. It's sort of like a lot of articles in the format of like a book that you can read, and they should be a very good beginning point. And if not, then I would highly recommend the book Quantum Computing for Everyone. I think it's a very easy read for a topic that can be as dense as quantum computing. Very well written. I am so glad to know that, this was useful in helping to understand what quantum computer is. And this raises actually a very interesting point where a lot of people are quite skeptical about quantum computers because some operations that have been done by quantum computers were actually way faster than classical computers and even supercomputers. But then we had some even better supercomputers which ended up beating the records of the quantum computers that were there. So the whole quantum supremacy, which is the concept which means that quantum computers are more efficient and more faster than classical computers, it's yet to be proven. But I think we're on the line where we can go ahead and prove that, because the thing is, if we right now we're struggling to create quantum computers with more number of qubits, and the more qubits we have in a quantum computer, the more faster the calculations are going to become, the more complex calculations can be done. And if that's achieved, then there can be quantum supremacy. But then again, at the same time, there's a paradox that it's hard to create quantum computers which are stable and have a big number of qubits. Okay, so that was an old question. And we have here, are there any remote jobs in quantum computing? I am not aware of any. If you find any, let me know. I would love to do a remote job in quantum computing as well. Can you join the Emirate Fellowship in Quantum Computing? I don't think there is any track right now in the fellowship which has quantum computing. I do know that a company that I mentioned before, Zandu, they run a summer fellowship. The applications for this year are obviously closed, but for next year you can always try to apply to this program. It's a 17-week summer program that you can look into. And I know that there's a very interesting hackathon happening. It's called QHack, and Zandu basically helps with a lot of other organizations as well, helps to organize it. So yeah, it happens online, so everyone can join it. I think it's a very cool event. They have a lot of interesting challenges, they have great prizes, so good hackathon to attend. Yeah, so this is everything that was at the top of my head about quantum computing. If you have any questions, please feel to put them down. If not, it'd be a good time to release all of you so that you can freshen up and be prepared for the next workshop or stream. Let me see if I just missed any question up here. Yeah, so in terms of reference resources, I named all these books and I told you about these courses. That is all I know of right now. Yeah, sorry. So one other thing that you might want to look on is Qiskit Global Summer School 2020. I think if you all want to look at videos, you can search for Qiskit Global Summer School. I found their videos to be really helpful in explaining me the concepts of quantum computing, and hope they can do the same for you. Yeah, it's been a lot of Qiskit advertisement. I swear this stream has not been sponsored in any way. But yeah, it's just a library that is easy to use. And they're doing good work with advocacy. So if anyone is interested in entering the more educative developer advocate side of things, Qiskit actually has a program which is called the Qiskit Advocate, and you can join that, be a part of the team, and help with all of the stuff that they do. Yeah, and if you all don't have any more questions, thank you so much for joining this session, for me, for sticking around, for asking great questions, and yeah, just being a part of this. Hope you all have fun. And tomorrow I'm doing a live stream on animations using JavaScript. So It's going to be, hopefully, it's going to be a fun session. Bye, all, and see you all later. Bye bye.